Let's integrate x cubed from 0 to 2. In this case, the function x cubed is a continuous function, therefore it's an integrable function. So all I need is just to start with a fine enough partition, and it won't matter how I pick those sample points inside the partition. My Riemann sum will be close to the true value of the integral. So I'll cut the interval from 0 to 2 into n pieces. Pictorially, I want to start with the interval between 0 and 2, and I want to cut it up into n pieces. Now, the length of this whole interval is 2 units long, so each of these pieces should have a width of 2 over n. And that lets me write down the formula. The cut point, x sub I, will be 2 over n times I. And that works out great. Right? If I is 0, then I'm at the left-hand endpoint, and if I is n, I'm at the right-hand endpoint, and in between, I'm just marching from the left-hand side to the right-hand side, moving 2 over n each time. Now, how should I choose my sample points? I'm just going to choose my sample points, x sub I star, to be the right-hand endpoints. So they'll be, in fact, the same as x sub I. Now I just have to write down the Riemann sum for this particular equal size partition and our chosen sample points. Now in general, the formula for Riemann sum is the sum, I goes from 1 to n of the function evaluated at the ith sample point times the width of the ith subinterval in my partition, right? This is the area of the rectangle. And I'm adding up all those rectangles to get an approximation to the area under the graph. Well, in this specific case, what do I have? X sub I star is the same thing. If I go back to this, x sub I star is the same thing as x sub I. So I can just plug in 2 over n times I. And x sub I minus 1, that's the width of the ith subinterval in my partition. But I rigged it so that all of the subintervals have the same equal width. They've all got width 2 over n. All right, so that's the sum that I want to calculate. Now the function in this case is the cubing function. So this is the same as the sum I goes from 1 to n of 2 over n times I cubed times 2 over n, which I could simplify somewhat. This is the sum I goes from 1 to n of 16, 2 cubed times 2, over n to the 4th, it's n cubed over n, times I cubed. So that's the particular Riemann sum in this case. Of course, this is just a specific Riemann sum for a specific value of n. To get the value of the integral, I'm going to take the limit as n approaches infinity. Yeah, the integral from 0 to 2 of this function x cubed is the limit as n goes to infinity of this Riemann sum. Now, strictly speaking, right, this integral would be a limit over all the possible partitions, but since the function's integrable, it doesn't matter what partition I choose as long as it's fine enough, and n going to infinity makes finer and finer partitions. So what I really want to calculate in order to calculate this integral is to calculate this limit. Well, let's see if we can do that. The good news here is that I've got a formula for the sum of cubes. So we will pull out that formula in a minute. And I've also got a constant here. 16 over n to the 4th is a constant, doesn't depend on I at all. So I can factor that out of this sum by distributivity. So this is the limit as n approaches infinity of 16 over n to the 4th times the sum of I cubed. I goes from 1 to n. And now I happen to know what the sum of the first n cubes is. And I can use that formula that we got from before. That's the same as the sum of the first n whole numbers squared. And in this case, that's the limit as n goes to infinity of 16 over n to the 4th times that's n times n plus 1 over 2. That's the sum of the first n whole numbers. And the sum of the first n perfect cubes is that squared. Now I've got to figure out what this is. Well, I can factor out a over 2 squared, and that'll cancel part of the 16. So this is the limit of n squared times n plus 1 squared times 4 over n to the 4th. And now this is the limit as n goes to infinity. This ends up being n squared times n squared plus lower order terms. So this is the biggest term here is 4n to the 4th over n to the 4th. So this limit ends up being equal to 4. And that is in fact the integral from 0 to 2 of x cubed dx. That integral is therefore equal to 4. Now what if I wanted to do this integral over some other interval? Well, I could repeat the same kind of calculation to deduce that the integral from 0 to 1 of x cubed dx is equal to 1/4, right? But that would be another whole calculation that I'd have to work out. Let's say I wanted to integrate over the interval 1 to 2. Well, here's a trick that you could use. So the integral from 0 to 2 of x cubed dx we already calculated, but forget the exact answer. What I want to note here is that this is related to 2 other integrals. Integrating from 0 to 2 x cubed dx is the same as integrating from 0 to 1 of x cubed dx, and adding to that the integral from 1 to 2. Now, geometrically, something like that hopefully makes some sense, right? If I draw a graph, here's 0, here's 1, here's 2. Here's the function y equals x cubed, say. This first integral from 0 to 1 is calculating the area here. Right? That's what this integral is calculating. The second integral from 1 to 2 is calculating this area here. Right? And if I add together these two areas, I end up getting the area from 0 to 2, which is what this integral is calculating. Well, the nice thing here is that since I know this integral and I know this integral, that's enough information to recover this integral. The integral from 0 to 2 we saw a moment ago is 4. The integral from 0 to 1 I'm claiming here is 1/4, and that's enough information then to tell me that the integral from 1 to 2 of x cubed dx, well, that must be exactly what I need to add on to 1/4 to get 4. That must be 15/4, right? So this red area in here must be 15/4 square units. What we're seeing here is that you can evaluate some integrals just by going back to the definition and using our knowledge of sums. But the sums are ugly, right? These are really terrible calculations. This is the exact same situation that we've been in before. A long, long time ago, we were faced with the definition of derivative, and we started computing some derivatives just by going back to the definition of derivative. But then over time, we learned a bunch of rules which made differentiation a whole lot easier. We're going to see the same thing happening here. Right now, we're just using these bare hand arguments to calculate integrals, but over time, we're going to develop more tools for evaluating integrals.